When we speak about the foundation of atomic identity, we are really speaking about the proton, because without it the idea of an element would not exist at all. Every atom in the universe carries a simple numerical truth at its core: the number of protons in its nucleus. This single fact decides whether an atom is hydrogen or helium, carbon or oxygen, iron or gold. No matter how atoms gain or lose electrons, no matter how they combine into molecules or break apart in reactions, their true identity remains fixed by the count of protons they contain. This makes the proton not just a particle among others, but the defining marker of matter itself. In the earliest days of scientific discovery, this idea was not obvious. Matter once seemed continuous, something that could be divided endlessly. As understanding deepened, scientists realized that atoms were discrete units, and later still, that atoms themselves had internal structure. When the nucleus was discovered, it became clear that most of the atom's mass and all of its positive charge were concentrated in an incredibly small central region. Within that nucleus, protons emerged as the carriers of positive charge, setting them apart from the neutral neutrons and the negatively charged electrons that surrounded the atom. From that moment, the proton became central to the story of what makes one element different from another. The concept of atomic number, now a basic principle taught early in science education, is in fact a profound statement about nature. Atomic number is simply the number of protons in the nucleus, yet it organizes the entire periodic table and explains the repeating patterns of chemical behavior observed across elements. Hydrogen, with a single proton, is the simplest and most abundant element in the universe. Helium, with 2 protons, behaves in a completely different way, stable and chemically inert. Carbon, with 6 protons, becomes the backbone of organic chemistry, capable of forming complex molecules essential for life. Oxygen, with 8 protons, supports combustion and respiration. Each step up the scale reflects the addition of 1 proton, and with it, a transformation in the possibilities of matter. What makes this even more remarkable is that the proton's role in identity is absolute. Electrons can be lost or gained, forming ions, but the element remains the same. A sodium atom that loses an electron becomes a positively charged ion. Yet it is still sodium because its protons have not changed. Even neutrons can vary in number, creating isotopes with different nuclear stability or radioactive properties. But the element's identity remains fixed. Only by changing the number of protons can one element become another, a process that requires nuclear reactions rather than chemical ones. This strict rule highlights how deeply the proton is embedded in the definition of matter. In natural processes, changes in proton number are rare because they demand enormous energy. Such transformations occur in stars, where intense pressure and temperature allow nuclei to collide and fuse. In these stellar furnaces, hydrogen nuclei, each consisting of a single proton, combine through a series of reactions to form helium and heavier elements. With each fusion step, the identity of matter changes, guided entirely by how protons rearrange themselves. The elements forged in stars are later scattered into space through stellar winds and supernova explosions, seeding future generations of stars, planets, and life. In this cosmic cycle, the proton serves as the unit of transformation, the counter that marks each stage of elemental evolution. On Earth, the stability of proton number is what makes chemistry predictable and reliable. Because the identity of elements does not change during chemical reactions, atoms can rearrange themselves into countless combinations without losing their fundamental nature. This allows complex systems to form, from crystalline minerals to biological organisms. The reliability of proton identity ensures that carbon atoms in living cells remain carbon, that oxygen remains oxygen, and that the laws governing their interactions remain consistent. Life itself depends on this stability, because biological processes require precise chemical behavior repeated trillions of times with minimal error. The proton also provides identity through charge balance. Its positive charge defines the electrical character of the atom's nucleus and determines how many electrons an atom must hold to remain neutral. This balance between protons and electrons shapes the size of the atom, the arrangement of its electron cloud, and its chemical reactivity. The structure of the electron shells, which control how atoms bond with one another, is ultimately a response to the number of protons pulling on those electrons. In this way, the proton indirectly governs not only what an element is, but how it behaves in the chemical world. At a deeper level, the proton's role in identity reveals a universe built on simple rules applied consistently. The fact that a single integer, the proton count, can classify all known elements suggests an underlying order to nature. This order allows scientists to predict the existence of elements not yet discovered, to understand trends across the periodic table, and to explore how matter might behave under extreme conditions. Even hypothetical elements created in laboratories follow the same rule. Increase the proton number, and a new element is born, however briefly it may exist. The proton's defining power also extends into modern technology and research. Particle accelerators are designed to manipulate protons precisely because their identity and charge make them reliable probes of matter. By smashing protons together at high energies, scientists recreate conditions similar to those just after the Big Bang, allowing them to study the fundamental laws that shape the universe. In these experiments, the proton is both subject and tool, a known quantity used to uncover unknown aspects of reality. From a philosophical perspective, the proton challenges our intuition about size and importance. Something so small, far beyond direct human perception, holds the key to defining everything we can touch, see, or experience. Mountains, oceans, living beings, and distant stars all trace their material identity back to arrangements of protons. This realization shifts our understanding of power and scale, showing that influence in the universe is not measured by size alone, but by position and role within the system of nature. As science continues to probe deeper into the structure of matter, the proton remains central. Even as researchers explore substructures within the proton itself, its role as the carrier of atomic identity remains unchanged. No matter how complex its internal dynamics may be, no matter how many particles and forces contribute to its behavior, the proton still serves as the unit by which the universe counts and categorizes matter. It is a reminder that complexity can arise from simple principles, and that the vast diversity of the material world rests on the stability of a single, positively charged particle. In understanding the proton as the foundation of atomic identity, we uncover more than a scientific fact, we uncover a narrative of order, continuity, and transformation. The proton stands as a constant through cosmic history, linking the birth of elements in ancient stars to the matter that forms our bodies today. Its presence defines what matter is allowed to become, setting boundaries and possibilities at the same time. In this quiet, unwavering role, the proton becomes one of the most powerful symbols of structure in the universe, proving that the identity of everything begins at the very heart of the atom. When the proton is understood as the foundation of atomic identity, its significance becomes even clearer when we examine how this identity governs change, continuity, and transformation across all scales of nature. Matter is not defined by appearance or behavior alone, but by an unchanging internal count that persists through almost every process the universe allows. This constancy gives the physical world reliability. Without it, atoms could randomly shift identities, chemistry would lose predictability, and complex structures could never endure long enough to evolve. The proton, by fixing identity at the nuclear level, makes long-term order possible in a universe filled with motion and energy. One of the most striking aspects of proton-defined identity is how it separates chemical change from nuclear change. In everyday life, we witness countless transformations: wood burns, iron rusts, food is digested, and cells divide. In all of these processes, atoms rearrange themselves, electrons shift positions, and energy is exchanged, yet the elements involved remain the same. Carbon does not suddenly become nitrogen, nor does oxygen turn into hydrogen. This is because chemical reactions do not alter the nucleus, and therefore do not alter the proton count. The proton acts as a boundary marker, drawing a clear line between surface, level rearrangement and deep structural change. This distinction allows matter to be flexible without becoming unstable. Only under extreme conditions does the universe permit the proton count to change. In the cores of stars, where gravity compresses matter to unimaginable densities and temperatures soar to millions of degrees, protons can overcome their mutual electrical repulsion. When this happens, they participate in fusion reactions that create new nuclei with different proton numbers. Through this process, the universe gradually transforms simple matter into complex matter. Hydrogen becomes helium, helium becomes carbon, and heavier elements are forged in later stellar stages or violent cosmic events. Every such transformation is a story of protons being added, rearranged, or converted, redefining atomic identity and expanding the chemical possibilities of the universe. This stellar origin of elements gives the proton a role that extends far beyond atomic classification. It becomes a record keeper of cosmic history. The distribution of elements observed in stars, planets, and living organisms reflects the history of proton-based transformations across billions of years. The carbon in human cells, the calcium in bones, and the iron in blood all exist because protons were once reorganized in ancient stars. When those stars ended their lives, they released newly formed elements into space, allowing future systems to inherit them. In this sense, proton identity connects the present moment to events that occurred long before Earth existed. The stability of proton identity also allows the emergence of complex patterns. Because atoms reliably maintain their elemental nature, large-scale structures can form without fear of internal breakdown. Crystals grow with repeating atomic arrangements, ecosystems develop based on consistent chemical interactions, and technological materials are engineered with precise properties. Engineers and scientists can design systems with confidence because the building blocks behave consistently. This predictability is not trivial, it is a direct consequence of the proton's role as a fixed identifier. If atomic identity were fluid, the very idea of controlled design would collapse. At the same time, the proton introduces hierarchy into nature. While atoms are made of smaller components, not all components play equal roles. Electrons govern chemical behavior, neutrons influence nuclear stability, but protons define what the atom fundamentally is. This hierarchy simplifies an otherwise overwhelming complexity. Instead of needing to track countless internal details to identify matter, nature uses a single number. This elegant efficiency suggests that the universe favors simple organizing principles capable of supporting vast complexity. Modern physics has revealed that even though the proton defines identity, it is far from simple internally. It is composed of quarks and gluons in constant motion, governed by quantum rules that defy classical intuition. Yet despite this internal complexity, the proton behaves externally as a stable, well-defined unit. This duality is one of the most fascinating features of nature: deep complexity hidden beneath stable simplicity. The proton shows that identity does not require rigidity, it can emerge from dynamic balance. Inside the proton, particles interact violently, yet the proton itself remains stable over timescales longer than the age of the universe. This stability raises profound questions about why the proton exists at all in its current form. Why does it have exactly the charge it has? Why is it stable rather than decaying? Why does it define identity so cleanly? These questions lie at the frontier of physics, touching on theories that attempt to unify forces and explain the fundamental constants of nature. Some theories suggest that proton stability is linked to deep symmetries in the universe, while others explore the possibility that protons may decay over unimaginably long timescales. Even if such decay exists, its rarity underscores just how robust proton-defined identity is. The proton's role in identity also reshapes how we understand change itself. True transformation, at the deepest level, is rare and powerful. Changing an element requires altering the proton count, which demands enormous energy and occurs only in exceptional environments. This makes elemental change a cosmic event rather than an everyday one. In contrast, surface-level change is abundant and accessible, allowing matter to adapt, combine, and evolve without losing its core nature. This layered structure of change, with the proton at its center, gives the universe both stability and creativity. In human exploration, this understanding has practical consequences. Nuclear technology, both constructive and destructive, is built on the manipulation of proton identity. Nuclear reactors release energy by splitting heavy nuclei, indirectly involving changes in proton-neutron arrangements. Particle accelerators create new elements by forcing protons into target nuclei, momentarily expanding the periodic table. Medical technologies use proton behavior to diagnose and treat disease, relying on the predictable identity and interaction of protons with matter. In all these applications, the proton's defining role is not abstract theory but practical reality. On a deeper level, the proton challenges how we define individuality and sameness. Two atoms of the same element may be separated by vast distances or participate in entirely different processes, yet they are fundamentally identical because their proton counts match. This universality creates a shared identity across the cosmos. A carbon atom on Earth and a carbon atom in a distant galaxy are, in essence, the same kind of thing. This idea unifies the universe, suggesting that the same rules apply everywhere and that matter is not fragmented into local exceptions. As science advances, new questions continue to emerge, but the proton remains a central reference point. Even when exploring exotic states of matter, extreme astrophysical environments, or the earliest moments of the universe, researchers return to proton identity as a guide. It anchors theories, organizes observations, and provides a stable language for describing matter. No matter how strange or unfamiliar a phenomenon becomes, counting protons restores clarity. In the end, the proton's role as the foundation of atomic identity reveals a universe that balances permanence and change with remarkable precision. It shows that stability does not come from immobility, but from consistent rules applied across time and space. The proton does not dominate through force or size, but through definition. By deciding what an atom is, it quietly shapes everything that atom can become, from the birth of elements in stars to the reliability of chemistry on Earth. The proton stands as a silent architect, ensuring that matter has identity, continuity, and meaning in an ever-changing universe. At the very center of every atom lies a region where immense forces operate in perfect balance, a place where stability is achieved not through stillness but through constant tension. This is the nucleus, and within it the proton plays a decisive role through its electric charge and its participation in the fundamental forces of nature. The positive charge carried by the proton is one of its most defining features, and yet it is also the source of a profound problem that the universe somehow solves. Positively charged particles repel one another, and inside the nucleus multiple protons are packed into an extraordinarily small space. By all ordinary rules of electricity, such a structure should instantly fly apart. The fact that it does not is one of the great stories of modern physics. The electric charge of the proton shapes atomic structure from the inside out. Because each proton carries the same positive charge, every additional proton added to a nucleus increases the electrical repulsion within that nucleus. This repulsion grows rapidly as proton number increases, threatening the stability of heavier atoms. At the same time, this same positive charge is responsible for holding electrons in orbit around the nucleus, creating the atom as a whole. In this way, charge is both a creative and destructive influence. It allows atoms to exist, yet it also challenges the integrity of their cores. The stability of matter depends on how nature resolves this contradiction. The solution comes in the form of another force, far stronger than electricity, but operating only at extremely short distances. This is the strong nuclear force, and it is the invisible glue that binds protons together inside the nucleus. When protons are separated by more than a tiny fraction of an atomic diameter, the strong force has no effect. But when they are pressed close enough, as they are inside the nucleus, this force overwhelms electrical repulsion and locks the particles together. The nucleus is therefore a zone of controlled conflict where repulsion and attraction coexist, and stability emerges from their balance. The proton's role in this balance is active rather than passive. Each proton contributes not only charge, but also participates in strong, force interactions that tie it to its neighbors. Neutrons, which carry no electric charge, play a crucial supporting role by adding attractive strong, force interactions without increasing electrical repulsion. This is why heavier nuclei require neutrons in increasing numbers. As more protons are added, the repulsive force grows, and additional neutrons are needed to stabilize the nucleus. The precise ratio between protons and neutrons determines whether a nucleus is stable, radioactive, or incapable of existing at all. This delicate balance explains why some elements are stable while others decay. In lighter elements, such as hydrogen and helium, the number of protons is small enough that electrical repulsion is easily controlled. In heavier elements, the competition between forces becomes more intense. When the balance tips too far toward repulsion, the nucleus becomes unstable and seeks a new configuration. This instability leads to radioactive decay, a process in which the nucleus releases energy and particles in an attempt to regain stability. At the heart of every such transformation lies the struggle between proton charge and nuclear binding. The proton's charge also determines how nuclei interact with one another. In nuclear reactions, such as fusion, positively charged protons must overcome their mutual repulsion to come close enough for the strong force to act. This is no small challenge. Under ordinary conditions, protons repel each other long before they can interact strongly. Only under extreme temperatures and pressures, such as those found in the cores of stars, do protons gain enough energy to approach one another closely. When they do, the strong force takes over, binding them together and releasing enormous amounts of energy in the process. This process of nuclear fusion illustrates the dual nature of the proton's charge. On one hand, it creates a barrier that resists change, preserving stability. On the other hand, when that barrier is overcome, it allows for transformations of tremendous power. The energy released during fusion comes from subtle changes in nuclear binding, where the combined nucleus is slightly more stable than its components. That small difference in stability is converted into energy, according to the laws of physics, powering stars and illuminating the universe. Inside the nucleus, protons are not static objects sitting quietly in place. They exist in a quantum environment, where positions are uncertain and interactions are governed by probabilities rather than fixed paths. The strong force itself behaves in ways unlike any other force. It becomes stronger as particles move apart within the nucleus, ensuring confinement, and weaker as they move closer, allowing a form of dynamic equilibrium. This strange behavior ensures that protons remain bound without collapsing into a single point. Stability, once again, emerges from balance rather than rigidity. The concept of nuclear stability reshapes our understanding of matter at the deepest level. Stability is not the absence of force, but the presence of opposing forces locked in equilibrium. The proton's charge continuously pushes against other protons, while the strong force pulls them back together. Neutrons help distribute this balance, acting as mediators that enhance attraction without adding repulsion. The nucleus exists as a tightly regulated system, sensitive to changes in composition and energy, yet remarkably durable over time. This durability is evident in the age of matter itself. Protons inside atomic nuclei can remain bound for billions of years without change. The atoms that make up rocks, oceans, and living organisms contain nuclei that were formed long before Earth existed. Their continued stability allows matter to persist and evolve without losing its fundamental structure. This long-term reliability is essential for the formation of planets, the development of life, and the continuity of physical laws across cosmic time. At the same time, the limits of nuclear stability reveal why the periodic table has an upper bound. As proton number increases, the electrical repulsion becomes harder to counterbalance. Beyond a certain point, no arrangement of neutrons can fully stabilize the nucleus. Elements with very high proton numbers exist only briefly, created in laboratories or extreme astrophysical events, before they decay. This sets a natural boundary on the kinds of matter that can exist, imposed by the properties of the proton itself. Understanding charge, force, and stability inside the nucleus has transformed science and technology. Nuclear energy, both in reactors and weapons, relies on manipulating the balance between repulsion and attraction. By splitting heavy nuclei or fusing light ones, humans have learned to tap into the energy stored in nuclear binding. Medical imaging and treatments also depend on nuclear behavior, using radioactive decay and proton interactions to diagnose and fight disease. In each case, the proton's charge and its role in nuclear forces are central to the outcome. On a conceptual level, the proton teaches a deeper lesson about nature. Stability is not guaranteed, it is achieved through precise conditions. A small change in charge, force strength, or particle arrangement could render matter unstable. The fact that the universe supports stable nuclei across a wide range of elements suggests that the fundamental constants of nature are finely tuned. The proton sits at the heart of this tuning, its properties perfectly suited to allow complexity without chaos. As we continue to explore the nucleus through experiments and theory, the proton remains a focal point. Its charge defines the problem of repulsion, its interactions embody the solution through nuclear forces, and its presence determines whether matter can exist in stable forms. The nucleus is a place of extraordinary tension, yet from that tension arises the solid world we experience. In understanding how charge and force interact within the nucleus, we come closer to understanding why the universe holds together at all, and why the proton, though unimaginably small, carries a responsibility of cosmic scale. When the balance of charge and force inside the nucleus is examined more deeply, it becomes clear that nuclear stability is not a fixed condition, but a continuous negotiation. The proton, by virtue of its positive charge, is always exerting pressure on the nucleus, pushing against every other proton present. This pressure never stops. It does not weaken with time, nor does it adapt on its own. What prevents the nucleus from tearing itself apart is the constant counteraction of nuclear binding forces that operate at precisely the right scale. Stability, therefore, is not a static achievement reached once and preserved forever, but an active state maintained moment by the laws of physics. This dynamic stability explains why nuclei respond so sensitively to changes in energy. When a nucleus absorbs energy, whether through particle collisions or radiation, the balance between repulsion and attraction can be disturbed. If the added energy is small, the nucleus may simply shift into an excited state, and then release energy to return to equilibrium. If the energy is large enough, the nucleus may undergo transformation, releasing particles or radiation in the process. These nuclear responses are not random. They follow precise rules determined by how protons and neutrons are arranged and how their forces interact. The proton's charge remains central in every case, defining both the resistance to change and the conditions under which change becomes possible. This sensitivity to balance is especially evident in radioactive decay. In unstable nuclei, the internal arrangement of protons and neutrons fails to achieve a sustainable equilibrium. Electrical repulsion may be too strong, or nuclear binding too weak, leading the nucleus to seek a more stable configuration. Radioactive decay is nature's method of correction. By emitting particles or energy, the nucleus reduces internal stress and moves towards stability. Whether this involves the transformation of a neutron into a proton, the emission of a charged particle, or the release of energy in the form of radiation, the process is always guided by the underlying struggle between proton charge and nuclear force. The existence of such decay processes highlights an important truth: not all matter is equally stable, and stability itself is a spectrum rather than a binary condition. Some nuclei are stable over timescales longer than the age of the universe, while others exist only for fractions of a second. The determining factor is how well the forces within the nucleus balance the proton's repulsive influence. This gradation of stability gives the universe both permanence and change. Stable matter forms the long-lasting structures of the cosmos, while unstable matter drives energy release, transformation, and evolution. In extreme environments, the balance of nuclear forces takes on even greater significance. In the dense cores of massive stars, matter is compressed to such an extent that nuclei are forced into close contact. Under these conditions, the repulsive barrier created by proton charge can be overcome repeatedly, allowing fusion to proceed beyond what is possible in smaller stars. As nuclei grow heavier, however, the cost of overcoming repulsion increases. Eventually, fusion no longer produces energy but consumes it, marking a turning point in the life of a star. This limit is set by the properties of the proton itself, particularly its charge and how that charge scales with increasing proton number. When stars reach this limit, the consequences can be dramatic. Massive stars may collapse and explode, creating conditions in which even heavier elements can form briefly before decaying. These catastrophic events redistribute matter throughout space, enriching the cosmos with elements forged under extreme force balance conditions. Once again, the proton's charge defines what is possible and what is forbidden. It sets the thresholds that govern stellar life cycles and cosmic chemistry. On a smaller scale, the same principles apply in human-made environments. In nuclear reactors, stability is carefully managed by controlling how nuclei absorb neutrons and release energy. Engineers rely on detailed knowledge of nuclear forces and proton interactions to maintain a controlled reaction. If the balance shifts too far, reactions can accelerate dangerously. If it shifts too far in the opposite direction, energy production stops. The proton's charge and its role in nuclear binding are therefore not abstract concepts, but practical factors that must be respected and understood. In medicine, similar precision is required. Proton-based therapies and nuclear imaging techniques depend on predictable interactions between charged particles and atomic nuclei. The behavior of protons as they move through matter, interact with nuclei, and deposit energy is governed by the same principles of charge and force that operate inside the nucleus. The reliability of these medical technologies rests on the consistency of nuclear physics, which in turn rests on the stable properties of the proton. At a deeper theoretical level, the balance between proton charge and nuclear force has influenced how physicists think about unification and symmetry. The fact that forces with vastly different strengths coexist and interact within the nucleus raises fundamental questions about why nature is structured this way. Why is the strong force strong enough to bind protons, yet short-ranged enough to allow atoms to exist without collapsing into dense nuclear matter? Why is the proton's charge exactly what it is, and not slightly larger or smaller? Even small changes could radically alter nuclear stability, eliminating many elements or preventing stars from shining. The observed balance suggests that the universe operates within narrow parameters that permit complexity. The proton's role in nuclear stability also shapes our understanding of time. Stable nuclei provide a form of material memory, preserving the structure of matter across immense spans of cosmic history. Unstable nuclei, by contrast, act as clocks, their decay rates marking the passage of time and allowing scientists to date rocks, fossils, and cosmic events. Both stability and instability arise from the same underlying interactions involving protons. In this way, the proton influences not only the structure of matter, but also our ability to measure history. As research pushes into new frontiers, such as the study of neutron stars or exotic forms of nuclear matter, the familiar balance between charge and force is pushed to its limits. In neutron stars, gravity compresses matter so intensely that protons and electrons merge into neutrons, drastically reducing electrical repulsion. These extreme objects reveal what happens when the usual rules of nuclear balance are overridden by gravitational force. Even in such cases, the behavior of matter can only be understood by starting with the properties of protons and the forces they normally participate in. Ultimately, the proton teaches that stability in the universe is an achievement, not an assumption. Matter holds together because competing forces are tuned in such a way that neither domination nor collapse occurs. The proton's positive charge introduces tension, while nuclear forces provide cohesion. From this tension arises the solid world, the energy of stars, and the possibility of life. By understanding how charge, force, and stability interact inside the nucleus, we gain insight into why the universe is structured rather than chaotic, enduring rather than fleeting, and capable of supporting complexity across scales that range from the subatomic to the cosmic. When we talk about mass and matter, we often imagine something solid, heavy, and tangible, yet the deeper science of mass reveals a story that is far more subtle and surprising. At the heart of this story stands the proton. Although unimaginably small, the proton is responsible for most of the mass of the ordinary matter that makes up the visible universe. Chairs, mountains, oceans, and even the human body owe their weight not to electrons or empty space, but largely to protons bound inside atomic nuclei. Understanding this connection reshapes our idea of what mass truly is and where it comes from. At first glance, it seems natural to assume that mass comes directly from the particles themselves, as if each particle simply carries a fixed amount of weight. But modern physics reveals that this intuition is incomplete. The proton does not gain most of its mass from the simple addition of the masses of its internal components. Instead, the majority of a proton's mass arises from energy, specifically the energy of motion and interaction among the particles inside it. This insight marks one of the most profound shifts in our understanding of matter. Inside the proton, quarks move at tremendous speeds, bound together by gluons through the strong nuclear force. These quarks are extremely light on their own. If we were to add up their individual masses, they would account for only a small fraction of the proton's total mass. The rest comes from the energy stored in their constant motion and the intense force fields that bind them together. According to the principle that mass and energy are equivalent, this energy contributes directly to mass. In this way, the proton becomes a concentrated knot of energy, masquerading as matter. This realization changes how we understand the substance of the universe. Matter is not primarily made of solid material in the classical sense, but of energy locked into stable patterns. The proton is one of the most stable of these patterns. It endures across billions of years, maintaining its identity even as it participates in countless interactions. The mass we associate with everyday objects is therefore a measure of how much energy is bound within protons and neutrons, arranged into atoms and molecules. The dominance of the proton in determining mass becomes especially clear when we compare it to the electron. Electrons are essential for chemistry and electricity, yet they contribute almost nothing to the mass of an atom. An electron is more than 1/800 times lighter than a proton. Remove all the electrons from an object, and its weight would hardly change. Remove the protons, and the object would cease to exist as matter at all. This stark contrast highlights how the proton anchors matter in the physical world. Because protons reside in the nucleus, they define the mass of atoms and, by extension, the mass of elements. Heavier elements contain more protons and neutrons, and therefore more mass. This relationship underlies the structure of the periodic table and explains why some elements are denser than others. It also explains why nuclear reactions release such enormous amounts of energy. When nuclei are rearranged, even a tiny change in binding energy can result in a noticeable change in mass, which appears as energy released into the surroundings. In nuclear fusion, such as the reactions that power stars, protons combine to form heavier nuclei. The resulting nucleus is slightly lighter than the sum of its parts, because some of the mass has been converted into energy. That energy radiates outward as light and heat, sustaining stars and enabling life on surrounding planets. In nuclear fission, heavy nuclei split apart, again converting a small fraction of mass into energy. In both cases, the proton's contribution to mass is central to the process. Without the mass-energy relationship embedded in protons, stars would not shine and nuclear power would not exist. The proton's role in mass also connects to gravity. Gravity responds to mass and energy, and because protons account for most of the mass of ordinary matter, they are the primary contributors to gravitational effects at everyday scales. The pull you feel from Earth, the way planets orbit stars, and the structure of galaxies are all influenced by the distribution of mass, much of which resides in protons. Although gravity operates on all forms of energy, the mass locked inside protons gives it something substantial to act upon. On a cosmic scale, the abundance of protons shapes the evolution of the universe. After the Big Bang, as the universe cooled, protons formed and became the building blocks of atomic nuclei. Their stability allowed matter to persist rather than dissolving back into radiation. As time passed, protons combined with neutrons to form nuclei, captured electrons to form atoms, and eventually assembled into stars and galaxies. Without stable protons carrying mass, the universe would have remained a diffuse sea of energy, incapable of forming structure. The persistence of the proton is therefore essential to the long-term existence of matter. Protons appear to be extraordinarily stable, with lifetimes far exceeding the current age of the universe. This stability ensures that mass remains locked into matter over cosmic timescales. If protons were to decay easily, matter itself would be temporary, and complex structures would have no chance to develop. The apparent permanence of the proton gives the universe a kind of memory, allowing matter formed billions of years ago to still exist today. At the level of human experience, the proton's contribution to mass is what gives physical reality its solidity. When you hold an object, its resistance to motion comes from inertia, which is directly related to mass. That inertia is, in large part, the inertia of countless protons bound together in atomic nuclei. The sensation of weight, the effort required to lift or move something, and the stability of structures all trace back to the proton's role in mass. Even in cutting-edge science, the proton remains central to our understanding of matter. Experiments that probe the internal structure of the proton aim to understand precisely how mass emerges from energy. These studies are not merely academic, they test the fundamental theories that describe the universe. By understanding how the proton's mass arises, scientists gain insight into the nature of the strong force and the deep principles that govern all matter. In reflecting on the proton's role in mass and matter, a profound picture emerges. The substance of the world is not built from tiny, solid beads, but from dynamic systems where energy, motion, and force combine to create stability. The proton stands at the center of this picture, embodying the transformation of energy into matter. It is small beyond imagination, yet it carries the weight of the world. Through it, the universe turns energy into structure and fleeting motion into enduring form. When the proton's contribution to mass is viewed in a broader context, it becomes clear that mass itself is not a simple property but an emergent one, arising from relationships rather than from isolated objects. The proton teaches us that what we perceive as weight is, at its core, the result of energy being held in place by force. This idea challenges the classical image of matter as something fundamentally solid. Instead, matter becomes a pattern of energy stabilized by interaction, and the proton is one of the most successful and enduring patterns nature has produced. This understanding has deep implications for how we interpret the physical world. Every time matter resists motion, every time an object requires effort to lift or accelerate, we are encountering the inertia produced by the mass of protons bound inside atomic nuclei. This resistance is not due to some internal hardness, but to the energy content of the system responding to changes in motion. The proton, packed with dynamic energy, becomes a primary source of this inertia. In everyday experience, this translates into the feeling that matter is substantial and real, even though its foundation is largely invisible motion. The relationship between proton mass and energy also reshapes our understanding of conservation laws. In nuclear reactions, mass appears to vanish or emerge, but in reality it is transformed. When protons rearrange themselves into new nuclear configurations, the total energy of the system changes. a decrease in mass corresponds exactly to an increase in released energy, and vice versa. This precise balance is one of the most reliable principles in physics, confirmed repeatedly in experiments and observations. The proton stands at the center of this balance, serving as a bridge between matter and energy. In astrophysical environments, this bridge determines the fate of stars and galaxies. The mass contributed by protons influences gravitational collapse, stellar ignition, and the long-term stability of cosmic structures. A star's mass, largely derived from the number of protons it contains, determines how hot its core becomes, how fast it burns its fuel, and how it will end its life. Smaller stars live long, stable lives, while massive stars burn quickly and die violently. These outcomes are not arbitrary. They follow directly from how proton mass interacts with gravity and nuclear forces. The same principle governs the formation of planets and other celestial bodies. Clouds of gas and dust collapse under gravity when their combined mass, again dominated by protons, exceeds a critical threshold. As matter gathers, pressure and temperature rise, eventually leading to differentiation, chemical reactions, and in some cases, the conditions necessary for life. The proton's role in mass, therefore, extends beyond the microscopic world into the architecture of entire planetary systems. On Earth, the proton's contribution to mass enables the existence of stable environments. Atmospheric pressure, ocean depth, and geological structure all depend on the mass of matter responding to gravity. Mountains stand because the rock beneath them has sufficient mass and strength to resist collapse. Oceans behave as they do because water molecules, containing protons in both nuclei and hydrogen atoms, have mass that responds predictably to gravitational forces. These large-scale phenomena are indirect expressions of the same proton-based mass that exists inside individual atoms. At the frontier of physics, scientists continue to explore how mass arises from the strong force that binds quarks inside protons. Advanced experiments use powerful particle accelerators to probe the proton's internal structure, mapping how energy and momentum are distributed among its components. These studies reveal that the proton is not a rigid object, but a constantly fluctuating system, where energy flows and rearranges itself while maintaining overall stability. The fact that such a system produces a fixed, measurable mass is a testament to the consistency of physical laws. This consistency raises profound questions about why the proton has the mass it does. If its mass were slightly different, the universe would look very different. Heavier protons would alter nuclear reactions, potentially preventing stars from forming stable energy, producing cycles. Lighter protons might reduce nuclear stability, making matter less durable. The specific mass of the proton appears finely suited to allow both stability and transformation, enabling a universe that is dynamic yet enduring. This delicate balance suggests that mass is not an accidental feature, but a critical parameter in the structure of reality. The apparent stability of the proton's mass also underpins measurement and standardization in science. Many physical units and constants rely on atomic properties that ultimately depend on proton mass. Precision measurements in chemistry, physics, and engineering assume that atomic masses remain constant across time and space. This assumption is supported by extensive observation, reinforcing the idea that the proton provides a reliable foundation for quantitative knowledge. Without such reliability, scientific progress would be severely limited. From a philosophical standpoint, the proton's role in mass challenges the distinction between substance and process. What we call matter is revealed to be a process stabilized by interaction, not a static entity. The proton embodies this idea perfectly. It is defined not by immobility, but by dynamic balance. Its mass is not a simple attribute but the result of ongoing motion and force. In this sense, the proton blurs the line between being and becoming, showing that persistence can arise from constant change. This perspective also deepens our appreciation of the interconnectedness of physical laws. The proton's mass is tied to the strong force, which governs quark interactions, and to relativity, which links mass and energy. It influences gravity, shapes nuclear reactions, and supports the existence of atoms and molecules. No single law or principle can fully explain the proton's role in mass. It emerges from the cooperation of many aspects of physics. The proton thus serves as a meeting point where different domains of knowledge converge. As research advances, new questions continue to emerge about the ultimate origin of mass. Some theories suggest that mass arises through interactions with fundamental fields, while others explore deeper symmetries that might explain why particles like protons exist at all. In all these investigations, the proton remains a central reference. Its measurable mass provides a benchmark against which theories are tested and refined. Understanding why the proton has the mass it does may eventually lead to a more complete picture of the universe's underlying structure. In the end, the proton's role in mass and matter reveals a universe where substance is born from energy and stability emerges from motion. Every object we encounter, from the smallest grain of sand to the largest mountain, is held together by countless protons quietly carrying energy in stable form. Their collective mass shapes gravity, resists change, and allows structures to persist across time. Through the proton, the universe transforms abstract energy into tangible reality, giving weight to existence itself and grounding the vast complexity of the cosmos in the behavior of a single, remarkable particle. When we look beyond the proton's role as a carrier of charge and mass, a deeper and more complex reality emerges, one governed by quantum rules that challenge everyday intuition. The proton is not a tiny solid sphere sitting quietly inside the nucleus. It is a dynamic quantum system alive with motion, interaction, and constant change. Its internal structure reveals a world where certainty dissolves into probability and stability arises from continuous activity rather than stillness. At the quantum level, the proton is composed of smaller particles known as quarks, bound together by force, carrying particles called gluons. These quarks are never at rest. They move at speeds approaching that of light, confined within an incredibly small region by the strong nuclear force. This confinement is absolute. Quarks are never found alone in nature. No matter how much energy is applied, they remain locked inside composite particles like protons. This phenomenon reflects one of the strangest features of quantum physics, where increasing separation does not weaken the binding force but strengthens it, ensuring that the proton remains intact. The behavior of quarks inside the proton cannot be described using classical trajectories. Instead, they exist as quantum states, spread out in space and defined by probabilities. Their positions and momenta are uncertain, governed by fundamental limits that prevent precise measurement. What we call the structure of the proton is therefore not a rigid arrangement, but a constantly shifting pattern of likelihoods. At any moment, quarks may appear closer together or farther apart, yet the proton as a whole maintains a stable identity. Gluons, the carriers of the strong force, add another layer of complexity. They do more than simply bind quarks together, they interact with one another as well, creating a dense and energetic field inside the proton. This self-interaction distinguishes the strong force from other forces in nature and contributes significantly to the proton's internal dynamics. The energy stored in these gluon fields plays a major role in the proton's mass and stability, making the proton a highly energetic object despite its tiny size. Quantum fluctuations further enrich the proton's internal life. At very small timescales, particles and antiparticles can briefly appear and disappear within the proton, contributing to its properties without violating physical laws. These transient components influence how the proton responds to external forces and how it interacts with other particles. The proton, therefore, is not just made of three quarks in a simple sense, but of a complex sea of activity governed by quantum principles. Spin adds another dimension to the proton's internal structure. The proton possesses an intrinsic form of angular momentum known as spin, but this spin is not simply the sum of the spins of its quarks. Instead, it arises from a combination of quark spin, quark motion, and gluon dynamics. This surprising result has driven decades of research, revealing that even basic properties of particles can have deep and unexpected origins. The proton spin is a reminder that quantum systems often defy simple explanations. Despite this internal complexity, the proton behaves externally as a stable, well-defined particle. This contrast between internal chaos and external order is one of the most striking features of quantum structure. The proton's identity does not depend on fixed internal arrangements, but on stable patterns of interaction. As long as the underlying quantum rules are satisfied, the proton remains a proton, regardless of the constant motion within. The quantum nature of the proton also influences how it interacts with other particles. When protons collide at high energies, as in particle accelerators, their internal structures become visible through the scattering patterns they produce. These experiments reveal that the proton's internal components share momentum in complex ways, further confirming that the proton is a dynamic system rather than a static object. Each collision offers a snapshot of the proton's inner life, shaped by probability and interaction. Understanding the proton's quantum structure has profound implications for physics. It tests theories that describe the strong force and challenges scientists to explain how stability emerges from quantum complexity. It also reinforces a broader lesson about nature. Fundamental objects are not simple building blocks, but intricate systems governed by deep laws. The proton exemplifies how the universe creates order not by eliminating motion, but by organizing it within strict constraints. In revealing the quantum structure and internal dynamics of the proton, science uncovers a deeper vision of matter itself. Matter is no longer a collection of solid pieces, but a tapestry of energy, motion, and interaction woven together by quantum rules. The proton stands as a powerful example of this reality, showing how something endlessly active can still serve as a stable foundation for the material world. From the smallest scale of atomic nuclei to the vast architecture of galaxies, the proton plays a central role in the network of forces that hold the universe together. It is not only a particle of matter, but also an active participant in the fundamental interactions that shape reality. Through its charge, mass, and internal structure, the proton connects different forces in a way that allows stable matter, energy flow, and cosmic structure to exist side by side. One of the most important roles of the proton is its involvement in the electromagnetic force. Its positive electric charge creates attraction with negatively charged electrons, forming atoms and enabling chemistry. This force operates over long distances compared to nuclear forces and is responsible for the structure of atoms, molecules, and all chemical bonds. Every material object, from simple gases to complex biological organisms, depends on this attraction. Without the proton's charge, electrons would not be bound, atoms would not form, and the universe would lack the rich diversity of matter we observe. At much shorter distances, the proton is deeply involved in the strong nuclear force, the most powerful force known in nature. This force binds quarks inside the proton and also binds protons and neutrons together inside atomic nuclei. It is this force that allows matter to exist in stable, dense forms. Without it, nuclei would disintegrate under electrical repulsion, and atoms heavier than hydrogen would be impossible. The strong force is therefore the hidden backbone of material existence, and the proton is one of its primary carriers. The proton also interacts with the weak nuclear force, a less intuitive but equally important interaction. The weak force governs processes that change the internal composition of particles, such as transformations between protons and neutrons. These processes are essential in stellar reactions and radioactive decay. In the hearts of stars, the weak force enables protons to begin fusion chains that ultimately release enormous amounts of energy. This energy is what makes stars shine and provides the conditions necessary for life to emerge on surrounding planets. Through this connection, the proton becomes a gateway between matter and cosmic energy. Gravity, though far weaker than the other forces, is profoundly influenced by the proton because of its contribution to mass. Since protons make up most of the mass of ordinary matter, they are key players in gravitational interactions. The accumulation of vast numbers of protons gives rise to stars, planets, and galaxies. Gravity gathers matter together, while nuclear and electromagnetic forces determine how that matter organizes itself internally. The proton sits at the intersection of these processes, helping translate microscopic properties into macroscopic structure. This interplay of forces reveals an important truth: no single force acts alone. The universe functions because multiple forces operate together, each dominating at different scales. The proton is remarkable because it participates in all of them. Its charge links it to electromagnetism. Its internal structure ties it to the strong force. Its transformations involve the weak force, and its mass connects it to gravity. Few entities in nature bridge so many domains at once. In this sense, the proton acts as a unifying element in the physical world. The balance among these forces is delicate. If the proton's charge were stronger, atoms would bind electrons too tightly, disrupting chemistry. If it were weaker, atoms might not hold together. If the strong force were slightly different, nuclei would either collapse or fail to form. Even small changes could eliminate stable stars or prevent the formation of complex elements. The proton's properties appear finely suited to maintain this balance, allowing the universe to be both stable and dynamic. On a cosmic scale, this balance shapes the evolution of the universe itself. In the early universe, protons formed as temperatures fell, allowing matter to separate from radiation. Their stability allowed atoms to form, leading eventually to stars and galaxies. Over billions of years, protons have participated in countless cycles of fusion, decay, and recombination, driving cosmic evolution while preserving the underlying structure of matter. The same proton that exists today has properties identical to those present shortly after the birth of the universe, highlighting a deep continuity in physical law. The proton's role in binding the universe is not only physical, but also conceptual. It demonstrates how complex order can arise from simple interactions repeated consistently. A single particle, following the same rules everywhere, can help generate immense diversity when combined in vast numbers. This principle extends beyond physics, offering insight into how stability and complexity coexist throughout nature. As scientists continue to explore the universe, from high-energy particle collisions to distant cosmic phenomena, the proton remains a central reference point. Its interactions reveal how forces cooperate and compete, how matter holds together, and how energy flows through the cosmos. In understanding the proton's role in binding the universe, we gain a clearer picture of why reality has structure rather than chaos, and why the universe is capable of sustaining matter, motion, and life across unimaginable scales of space and time. The story of the proton does not end inside the atom or even within the nucleus of a star. It extends outward into the grand narrative of cosmic evolution and inward into the delicate processes that make life possible. From the earliest moments of the universe to the chemistry of living cells, protons have been constant companions in the unfolding of complexity. Their presence links the birth of the cosmos to the emergence of consciousness, revealing a deep continuity between the largest and smallest scales of existence. In the aftermath of the Big Bang, as the universe expanded and cooled, protons were among the first stable particles to form. Their survival marked a turning point, allowing matter to persist rather than dissolve back into pure energy. As temperatures dropped further, protons combined with neutrons to form atomic nuclei and later captured electrons to create the first atoms. This sequence laid the foundation for all subsequent structure in the universe. Without stable protons, the early universe would have remained a formless sea of radiation, incapable of developing stars, galaxies, or planets. As gravity gathered clouds of hydrogen, composed mainly of single protons, the first stars were born. Inside their cores, protons collided and fused, releasing energy and creating heavier elements. These stellar reactions were slow and precise, governed by the balance of forces that allow protons to overcome their natural repulsion. Over millions and billions of years, stars transformed simple matter into complex matter, forging the elements necessary for planets and life. When stars exhausted their fuel or ended in explosive deaths, they scattered these elements into space, enriching future generations of stars and planetary systems. On newly formed planets, protons continued their role in shaping complexity. In water molecules, protons enable hydrogen bonding, a subtle but powerful interaction that gives water its unique properties. These properties make water an ideal medium for life, allowing chemical reactions to occur efficiently and supporting stable environments. The behavior of protons in water influences temperature regulation, nutrient transport, and countless biochemical processes. Life as we know it is inseparable from the way protons behave in this simple yet extraordinary molecule. Within living cells, protons are not passive components, but active agents of energy flow. Cellular respiration, the process by which cells extract energy from nutrients, relies on proton gradients across membranes. By controlling the movement of protons, cells convert chemical energy into usable biological energy. This mechanism is remarkably efficient and universal, found in organisms ranging from bacteria to humans. The proton, in this context, becomes a carrier of life's energy, linking physics to biology in a direct and tangible way. Protons also play a crucial role in maintaining the structure of biological molecules. The shape and stability of proteins, DNA, and other macromolecules depend on interactions that involve charged particles, including protons. Small changes in proton concentration can alter molecular behavior, influencing enzyme activity and genetic expression. This sensitivity allows life to be responsive and adaptable, but it also underscores how deeply biological function is rooted in fundamental physical properties. The influence of protons extends even into human perception and experience. Nerve signals, muscle contraction, and sensory processes all depend on the controlled movement of charged particles, while electrons often take center stage in discussions of electrical signaling. Protons contribute to maintaining the chemical environments that make such signaling possible. The stability and reliability of these processes depend on the consistent behavior of protons under a wide range of conditions. From a cosmic perspective, the universality of the proton is striking. A proton in a distant galaxy is identical in every measurable way to a proton on Earth. This uniformity ensures that the same physical laws operate everywhere, allowing scientists to interpret distant astronomical observations using principles tested locally. It also suggests a deep unity in the universe, where the same building blocks give rise to stars, planets, and life across vast expanses of space and time. The connection between protons and life highlights an important lesson about emergence. Life is not separate from the physical universe, but arises naturally from its properties. The same proton that participates in nuclear fusion in stars later becomes part of a water molecule, a protein, or a cell membrane. This continuity blurs the boundary between cosmic and biological evolution, showing that life is a natural extension of matter organizing itself under consistent rules. As research continues into both cosmology and biology, the proton remains a key point of intersection. Studies of the early universe, stellar processes, and fundamental forces inform our understanding of life's origins, while biological systems provide insight into how physical principles can be harnessed for complex function. The proton stands at the center of this dialogue, a constant presence in an ever-changing universe. In tracing the journey from stars to living cells, the proton emerges as a quiet but essential architect. It fuels stars, shapes planets, drives biological energy, and supports the chemistry of life. Through its stability and versatility, the proton links the history of the cosmos to the story of life, reminding us that the same fundamental particles that light the stars also sustain the processes that allow us to observe and understand them. The deeper scientists explore the proton, the more it reshapes our understanding of reality and our place within it. What once seemed like a simple, positively charged particle has become a gateway to some of the most important questions in modern science. By studying the proton, Researchers do not merely learn about a component of the atom, they uncover principles that influence physics, chemistry, cosmology, and technology. The proton stands as a reminder that understanding the smallest elements of nature can transform how we comprehend the largest structures and the future of human knowledge. One of the most powerful ways the proton reshapes modern science is by serving as a testing ground for fundamental theories. The strong nuclear force that governs the proton's internal structure is described by complex mathematical frameworks that push the limits of human understanding. By probing how quarks and gluons behave inside the proton, scientists test whether these theories truly reflect reality. Every precise measurement of proton behavior becomes a critical experiment, either reinforcing current models or revealing gaps that point toward new physics. The proton also plays a central role in the search for unification in physics. Modern science seeks to explain nature through a small number of fundamental principles rather than a collection of disconnected rules. Because the proton participates in all major interactions, electromagnetic, strong, weak, and gravitational, it becomes a natural focal point for unifying theories. Understanding why the proton has the properties it does may offer clues about deeper symmetries that govern the universe, potentially leading to breakthroughs that connect forces once thought to be separate. In cosmology, the proton provides a bridge between the early universe and the present day. Observations of distant galaxies, cosmic radiation, and elemental abundances all depend on the behavior of protons under extreme conditions. By understanding how protons formed, interacted, and survived in the early universe, scientists can reconstruct the sequence of events that led to today's cosmic structure. This knowledge transforms abstract theories of the Big Bang into testable models grounded in particle physics. The study of the proton has also driven technological innovation. Particle accelerators, detectors, and computational tools developed to explore proton behavior have found applications far beyond fundamental research. Medical imaging, cancer treatment, materials science, and even data processing have benefited from technologies originally designed to study subatomic particles. In this way, the proton has indirectly shaped modern society, turning curiosity-driven research into practical advancements that improve human life. The proton's influence extends into precision measurement and standards. Because its properties are stable and universal, the proton serves as a reference point for defining physical quantities. Experiments that rely on atomic and nuclear properties depend on the consistency of proton behavior across time and space. This reliability allows science to build a cumulative body of knowledge, where results obtained in one laboratory or era remain valid and comparable in another. Without such stability, scientific progress would be fragmented and uncertain. At the frontier of research, the proton challenges scientists to rethink the nature of simplicity. Although it appears elementary in everyday descriptions, the proton is anything but simple. Its internal dynamics reveal layers of complexity that emerge from underlying rules. This challenges the notion that understanding nature means reducing it to smaller and simpler parts. Instead, the proton shows that richness and complexity can arise even at the most fundamental levels, encouraging new ways of thinking about reduction and emergence. The proton also influences how science approaches the unknown. Questions about proton stability, possible decay, and behavior under extreme conditions drive experiments that explore timescales and energies far beyond ordinary experience. These investigations expand the boundaries of what can be tested and observed, pushing science into regimes that were once purely theoretical. Each new result refines our understanding of what is possible in the universe and what remains mysterious. Beyond its scientific impact, the proton carries philosophical significance. It illustrates how the universe can be governed by consistent laws that apply everywhere, from the smallest particles to the largest cosmic structures. This consistency invites a sense of unity in nature, suggesting that the same principles that shape distant galaxies also operate within the atoms of our own bodies. The proton becomes a symbol of this unity, connecting human understanding to the fabric of the cosmos. As research continues, the proton remains both a foundation and a frontier. It anchors existing knowledge while pointing toward deeper questions yet to be answered. By studying the proton, scientists refine their tools, challenge their assumptions, and expand their vision of reality. The journey into the heart of the atom does not end with understanding what the proton is, but with discovering what it can teach us about the universe and our place within it.